Hello, everyone. I'm Game Dev Micah. Thanks for coming to this talk. This is the first talk tonight, of course, or today, I guess, on less is best, UEFN static level optimizations. Now, I have 250 slides. Isn't that nice? I don't do animations, so I'm just getting through bullet points, but I get to say I have 250 slides. I'm doing another talk tomorrow on destruction for UE5, so I'm kind of doing static environment with this, and then full motion environment with that. So very harebrained, getting both sides. A little bit of my history here, just to give you on it. I've been doing independent game dev since 2007, just mainly in a monk in my basement, looking at all the different ways to do things, starting off with Unity, ECS dots, the data-oriented programming thing, then getting fed up with Unity yanking the rug out from underneath me, came over to an enterprise-grade service here at Unreal. It's been amazing. So prior to that, just a little bit, I came in over at 4.22, started working on Fortnite just last year, doing just optimization. So what this talk's going to do, it's going to look at some of the background from Unreal Engine side of it to help you see what's going on in the black box that you can't from the Fortnite side of the world. So I'm going to try to show that black box to you. I have a Nanite plugin on the Fab Store, just to sort of show I'm doing that to enable Nanite on Niagara. So Niagara particles being rendered as Nanite being brought into that. So that's where my destruction stuff's at. I have released 2 Teenage Mutant Ninja Turtle levels. 5 players. Hey, thank you. So I've gone through the whole process with 2 of those, so that's great. Things are pretty well optimized out there. I mean, until you get really detailed. So, this is going that extra step is what we're going to be talking through. You don't have to do any of this stuff, but I want you to be aware of it. I want to open your eyes to some things. We're all in different, so I'm going to try and do that. Prior to coming back here, so I did 25 years of data centers. So I'm going to talk about the Fortnite infrastructure a little bit, show you some visuals of how the servers work too. And then schooling background, programming, business, administration, stuff like that. Thank you. I'm a dad, 2 boys, Luke and Logan, so a little bit of a nerd. My wife is too. It's my mom down there. Data center stuff. I worked with, one of my neat ones was Intel, top 400th most powerful supercomputer in 2 cabinets, 0.75 kilowatts. That's really a lot of power. But back in 2013. And I have cars from that too. I used to do esports with Battlefield Vietnam with Team Warchild. We won everything. So I did that after working on Counter-Strike. And my first level on Counter-Strike was a destruction level, DE Dam. So the destructions come a long way. And then Tim has retweeted my destruction too. So if you know about that, I'm working on destruction in the matrix sample. So that's been a huge blessing. So there's me. So this talk is titled Less is Best. Always reduce your instructions. And we're going to go fill a lot of slides on that. What are we talking about here? So I say PNG data. Think about like a picture or your texture piece, all right? You have that on your disk, this data. Then you have your shader instructions. That's all the different things you're putting in that material. That combines into cycle time on your processor. So the more data, more instructions you have, the longer the frame's going to take to complete, less frames you're going to get. That's on the server and also on clients. And we'll go through that. That's why I say, sorry, I might speed through. Oh, and all these slides I'll be giving you at the end. They're already up on my link, so I'll give you a link. So you can go ahead and go through all these pieces. Execution happens in a couple different places. Say on your GPU, on the processor, and we'll look at that. And optimization is, once again, reducing what these data are. So smaller pictures, less instructions to make it look like you want. And I like RE, and so I get to get an RE pin or acronym to always reduce instructions. So we're going to go through really quickly, and then we'll go through more later terms, just to make sure we're synced. HLODs, what are these? These are hierarchical levels of detail. They're systems that look to reduce down the complexity of your scene, but keep the visual the same. World Partition is a system that builds HLODs for you. They do 2 types of HLODs. Instant static mesh, which is foreign because UEFN props don't support it, so we'll talk about that, and a merge mesh, which we're going to go through and look exactly how it impacts your packages, size, which is one of the bigger things if you don't use custom props. It's a custom prop. Your HLOD merge mesh is a custom prop. And it does a runtime transition between the 2. You probably know that, the spatial loading distance. On the client, you can bring in out actors. Here's an example of what happens in these HLODs. So with merge mesh on the left side there, that's all your actors, all your components, everything. On the right, that's the simplified, like the lowest level of detail, no interactable devices that are put in something that you can see far away. static mesh components and static mesh lods. So if you have just a static mesh, it's going to have one mesh in there with one set of vertices, one level of detail. You can add level of details, which the props do, to reduce down the data and the complexity that you see rendered. And so you actually have 3 separate messages, or however many lods you have, so you have 5 different levels of details. You're storing 5, if it's a custom prop, or even in the Fortnite prop, you're storing 5 different meshes, maybe 5 different materials, and that all goes into the stuff that has to be processed across your servers and your clients. So it's just that compiling of detail. What is an ISM then? So we have a single mesh component, a LOD for a mesh component has a bunch of meshes on it. An ISM will take a single mesh and take a bunch of transforms for it and send it to the GPU in one batch, rather than say you have 3, we'll go into some detail. So it's batching them together, but the same mesh, no reduction of triangles. HISMs have multiple ISMs with a lower detail mesh on them. So it's storing all the extra data and picking which one to do to increase rendering speed, but you have more data you're storing. FISM, foliage ISMs. These are meant for grass. So sometimes if you try to put a tree into it and bake it in the HLOD, it's just not meant to go that way. So just think about foliage ISM as just stuff that won't make it at a long distance away. Nanite, unification of rendering, but it doesn't work on phones. So I'll mention that we just can't use it overall. Hopefully when they get it up to it, it's lovely, I love it, but we just can't use it. So then when you're doing these HLODs, when the world partition is going on, you have grid cells. These are how much of the space gets merged into a single mesh or ISMs to help reduce that complexity and get rid of those actors at distance. Level streaming is the term used just to transition between those HLODs and back to the actors. It's not like a new system or anything. It's just saying we're going to stream that simplified mesh in or bring in our actors. It's just a term. And world partition triggers level streaming, but just local to the player. So if spatial loading will unload actors and devices on your client, but not the server. So the server is going to still have to consider those devices and things sitting on it. And we'll go through that detail. Data layer, okay, let's just get rid of it. We'll talk about that in a minute. Spatial loading here. So client side only swapping. So when you enable this, the client side will lighten up what it has to look at, what it has to cycle, what data is on the client side. But the server loads everything and keeps it there all the time. Culling helps you reduce the visuals for things that you do have spatially loaded on the client. Because what happens is you're sending data in a draw call, and we'll talk about draw calls, to your GPU to actually make the image. So the less draw calls you send, the less data you're sending to the GPU, the less the GPU has to process it to make the frame rate. So just reduce it down. So like we see little pieces out in the distance get taken away, because maybe we don't need that detail, and then the system and the servers, the rendering doesn't have to consider it to do the draw call. This you can set on your all your components. And I'll talk later about how live edit resets it. Data layers, I knew a little bit about them, but when doing the talk, I'm like, this thing is extremely important, because what data layers let you do is unload actors on the server side. So if you have an area or cells that don't have players in them, you can use data layers to unload those devices, then your server doesn't have to process that data. So just reducing that data down. That will get faster server tick rates. Scene graph, that's coming up. It's a light, and I'm like, I'm giving this talk. Scene graph looks amazing after the keynote. But yes, it's a lighter than actor-based system, really looking towards mass or Unity's ECS, where you have the least amount of data to represent each piece. So we're heading in the exact same direction in this talk, just less information. So let's talk about draw calls. A draw call is when the CPU asks the GPU to render an object or a component, so any component. AKA a call for drawing a specific object. And then it sends that data to be rendered. So if we looked at a tree, I have 2 components for my tree, my leaves, my bark, I have a leaf texture, a bark texture, I have my transform. That's 2 draw calls for the 2 components and the 2 materials. So I would batch that data up, send it to the GPU would draw those twice, and I get my frame rate, and it would tax my storage, RAM, the CPU, the GPU to pull and move this data around. So the less of it you have, the lighter those textures are, the lighter the models are, the less you're pushing around. And the draw calls are sent at the end of the frame. So you have to do all your work on the client side before you can tell the GPU to do all the drawing work. So it's really, they're serialized like that. When you reduce your draw call requests, there's less work to be done on the GPU each frame, and it results in faster frame generation, which is more frames per second. So you get a draw call per component. We're going to talk about every rendered thing. I feel like this is standard rendering is what I'm trying to say here, which is if you have 2 tree actors, 4 components, 2 trunks, 2 branches, you're going to have 4 draw calls for each component, each material. 10 trees, 20 components, 20 draws. 100 trees, 200 draws for 200 components, an actor with the trunk and the tree on it. This is standard rendering. This is what we get on the mobile and everything like that. How do we improve it? If we go to instancing, so with standard rendering, we have all these components. We have 100 trees, 200 components for the 2 meshes. With instances, we have the mesh for the tree and the trunk, and we have the textures, but we're sending in batches of locations, so we just continue to get the same 2 draw calls because we just have 1 component with 2 meshes. If we were to have 2 components, so here we're going with 1 ISM on the left for 2 draw calls. Here we have 2 ISMs of 50 instances each instead of 100. We get double the draw calls because those components don't get to batch together. And you see here, basically, we have 100 components instead of 2. And it multiplies that out. Sweet. ISMs 100 to 1 on draw calls. Why don't we just use them all the time? Why not instance everything? Well, they're not interactive. You can't break them. You can't build with them or any of that stuff. If you're using instancing, it has to be completely static. You can put them on interactable items, but I'm saying you can't modify the array of locations at runtime. So what about Nanite? So we're trying to reduce down our draw calls. So if you have a Nanite mesh, you can have a whole bunch of components because those components get merged into a single component, which is the Nanite mesh. And then it's just your textures, or your materials rather, your custom materials that become the draw calls. So we have a trunk material and a tree leaves material. Doesn't matter how many instances we have of it, it's always just going to be 2 draw calls for those 2 materials. Always reduce instructions. So the REPs like to sort of hammer us in there. We're trying to reduce down instructions and reduce down data. So each component adds cycles and data when it's in each option. So I took here is this a basic actor, like just you create a base actor. It still has, including HLOD to be considered in there. It still has can be damaged to be considered in there. That means that these actors on the server side have to be checked, even a little bit infrequently. But if you don't need this actor to be damaged, why are we considering it? So that's what when you think about less is best is like, what options do I disable? I know I don't need this. This thing's never going to be damaged. So disable what you don't require. So larger props, there's a lot more things on there. So if you have a building or a wall that you don't want to bounce or take damage, disabling those pieces or clearing out the sound if you're not playing sound on there will prevent that from being linked and prevent things from being cycled. It'll reduce your data. And that's what these little cycles I'm doing here is saying each option enabled is making more work. If you wanted to adjust settings on a lot of actors, there's a beautiful tool called the bulk property matrix or edit components of property matrix. If they're the exact same actor, you can pick subcomponents and work on them in a grid or a group. So you can replace a lot of things of the same like really quick. So like if you select a bunch of them, you can go ahead and turn off generating overlap events if you don't need overlap events. Physics are not going to be looking for that every frame on the server, not costing you, or on the client as well. So let's look at some examples. In the base engine, we get options to use a program called Unreal Insights. And so I've spawned 20,000 actors with a movable light like Fortnite has. And we're going to look at the impact of just a couple settings on them, right? So 20,000 actors set as a movable mobility so that they may move. Not that they're enabled for physics or anything, just that they might move at some point. We can't unify draw calls. We get 20,000 draw calls. If we go and we just set them as static, it reduces down to 1,600. And the reason for that is something called automatic dynamic instancing. So Unreal goes ahead and scrapes the game and looks for matching instances that are in the same mobility type. and then can batch them into ISMs for us. So it's so much of an improvement, they do it already in the engine automatically every frame. If we went to HLODs, which made and compressed those static 20,000 objects into just a few ISMs in different cell sizes, we have a reduction in draw call. And you can see the frame rate right across the board. All these numbers here, like frame 21, frame 15, frame 8, those are more quickly the frames are being produced, so we get better frame rates. But we get the same visual, same collisions, everything's exactly the same, non-interactable, of course. So we're going to look at insights here about those 3 different options: movable enabled, set to static, or an HLOD. And how insights work is the bigger the bar is, the longer it's cycled, and so the less frames you're getting. So here on the far side, we go from 22 to 15 to 3. And what that happens is you see we have this large bar on the side that says end physics. That is just because it's movable, that we're checking to see if it was moved. And that's every frame for 20,000 actors. And it's just an actor in a static mesh. If we just set the static, that goes away. And then if we go to ISM, it gets even teenier. And then with rendering down here, it's the same thing for occlusion culling. So all the work we're doing out there, rather than doing work on 20,000 actors individually, it's now like 5 actors with this HLODs, or 5 components to check. And if we do it by hand, meaning rather than having cells out there in the grid area, we just have one ISM because we know it's only one cube that we're working with, we're going to have one draw call. It says 36. That's actually the draw calls for the output we're seeing there, the frame rate and stuff. So you can see, like, if we had 20,000, it has 35. Here it's just 36. So it's just one draw call for all 20,000 of those boxes of the same mesh, same material. And the frame rate's the best there. We're at 120, you can't beat it. So what if we just hid the actors, because it sounds like a frame rate thing? Between movable and static, we're still checking physics. Also, you're still going to spatially load those things in and out. So you can have that spatial load in and out hit too if they're spatially loaded, even though they're invisible. So how does this actually, here's a visual of it. The data cycles, that would be whatever you're bringing in, and then the cycle there would be your frame time at the top. So how many frames? And so if you want shadows on something, it takes a little bit more time. It's a bigger amount of data. It's going to slow the rate down a different amount. So what I'm saying here is not everything's equal. You know, if you don't need shadows on something, it might be a really big improvement. You're like, well, why wouldn't I need shadows on it? Small items, or a mountain really far away. Block diagrams. Okay, pretty nerdy here. What is a frame time? So what's going on? Your processor or your motherboard gives you these printouts when you're building a system that's saying how data flows. So you have a couple different hard drive choices, NVMe, SSD, and some iron down there. I'm showing them how slow it is to actually transfer 1 gig just to move it off the hard drive over to your coprocessor. The coprocessor's there because everything's so slow below it, it's got to pile up the data to send it up to the actual processor RAM to talk at 32 gigs per second. And that's just us physically moving this data, moving these instructions around to do the work. And so there's a real contention going on here, trying to show different colors, different amount of bandwidth. I had this all animated and stuff too, but it's nice just to have pictures. And you're getting in there, and you're adding more to it with every option you check off. Adds to the cycle time. Fortnite's a client-server environment, so let's look at it all the way through. Here's what data cycles look like at the whole environment. Frame time completes per second on the server, right? So we have server ticks. So the CPU is considering everything that's not unloaded with a data layer. And then it sends out a network frame at some rate separate from the CPU frame. That hits the client gets its update, it will send a network frame too back, and then it has its own cycles. And only the client has a GPU frame. So only the client is trying to actually render the image. You don't get a dedicated server. So your motherboard we were just looking at earlier, you're sharing it with a bunch of other virtual machines, other Fortnite players perhaps, or other Fortnite servers. Linux is sitting up there with Unreal sitting on it with just Fortnite. You have your data cycles feeding into it, so the frame time is having to compete with other virtual machines. And that's your devices that are causing that type of cycling. So anything you have out there is feeding it up more data to have to crunch to make a frame and send out to everybody. And I have multiple VMs up there, multiple Unreal, because these are all of our islands. And these are also Netflix. I don't know if I can say a name like that, but people know that they're on Amazon, so okay. But they're competing with them for the resources. Because it's not just one physical hardware, it's a lot of physical hardware, and it's all being shared. So the more you reduce down your data and your requirements on it, the quicker your stuff, your server, can operate in there and get around the other things. Server racks, so you get just big old buildings filled with this, multiple buildings. Goes out to the internet, goes out to all your different players and all your different devices. All this has cycles. All the data has to go in here, go into pools. Delay is the more data, the more infrastructure that you have to tax. Always reduce your instructions. Get rid of this stuff. So let's look at actual merge meshes and how to reduce something, reduce down what we're looking at. Here you can see HLODs far away are the more simplistic view, and near we get all these actor pieces. And the landscape excluded. I'm looking at tilted towers. I was thinking we might, all have picked it up at one point or another. Here's a bunch of actors that are excluded from being put into HLODs, minus the trees. The trees are in the HLOD. They're spatially loaded, and that means they're always loaded on the server, so that you can always have their state unless you unload them with data layers. Clients can unload these with spatial loading distance, which helps their data get smaller, so they can render better frame rates. Loaded components on the clients are taking up data, taking up cycles, delaying frame rates. So we're going to talk about what we can make static versus what we can make non-static. And static just means if it ever changes or not. Static would be it never changes. So, so data layers and verse pooling are some of the most powerful things out there. That means if you so data layers will unload actors from the server, which means we'll actually take that data away. You can put them in two different states, or three different states, loaded or unloaded, and those won't be visible, so you won't have to deal with the rendering data. Or when you make them visible, now you have to deal with the rendering data too. Using data layers to unload components and actors when the player leaves an area, or when you finish an event, like to get rid of a skeletal mesh or a sequence that you were dealing with, get that data off the server, off the consideration for the server. Yeah. And clients too. First pooling. I don't know where that's an extra icon up there. I don't know where that came from. So verse pooling is teleporting a smaller set of devices around between needed locations. I've seen examples from doing consulting with a few of you, so thank you very much, about using that to do teleport devices or lockers or vending machines. So think about if rather than having a million vending machines around your map of similar items, when a player is near it, triggers an event, transports it there. Reduces down the amount of devices you're using. But you have to do it in verse. And you want to keep some sort of a representation there. So like if it's a teleport or something, some sort of a mesh or something there so that as they walk over it, they know it's still there, even though the actual device isn't there. Why exclude components from HLODs? To reduce that data. So like the small rocks you may never put in HLODs. They'll be spatially loaded in, but you just don't put it into the HLOD to reduce down triangles. All moving components are typically excluded from HLODs because if the HLOD sees it's movable, it's expecting it could move. So it says it won't be stuck there. And small things too. Exclude that because you just might not be able to visually see it, so you don't need that data there. Reduces the amount of triangles and materials in that merge mesh, and we're going to look at the actual size of the merge mesh. So how do you go about baking these HLODs? You go ahead and enable any component you want to have included in it, and you pick a batching policy. You go ahead and build your HLODs, and I always delete before building, and it's just been so nice after that. I haven't had any issues with it, so I'd always recommend deleting before building. What it builds, it takes the highest level of detail, the least amount of triangles, and merges it into one mesh. And what that means is that these higher ones here with shutters, that's adding more and more detail in. So you can see Epic and just how this all works is about getting the least amount of detail. It's all about simplifying the scene. Any items that may change, we talked about this. You exclude them. Destroyed buildings, walls. Yeah, so what's sort of the downside? is that you do have all these things are destructible. If you go out and break a building at the HLOD distance from when you step away, the building's there again. When you go over to it, it's gone. That's an inconsistency. That's just part of the beast. If you want things to be modified like that, exclude them from the HLOD so that they're there anyway. So yeah, exclude interactable things, not spatially load them. Keep actors loaded on clients all the time. And the max draw distance would then be what you could do to tune down when that thing's hitting your rendering part. So replication then dictates rendering because it has to actually get the item over to you. And we don't have access to know what the replication range is, sadly. So it's kind of a replication and spatial loading battle with each other. And this is, we covered very quickly earlier about these terms. Now I'm just going into them into more detail. So with the max draw distance, you can go in any item and go ahead and set this, and it will help you get rid of the consideration for rendering that on the GPU when it does the sending draw calls. So we're reducing draw calls. And you can set them all items, but if you go into live edit, it will reset it. So let's look at the package size impact of using HLODs. So in Tilted Towers, 46 megs is 46.7 megs is the size of the folder that Tilted Towers is. When you just build the default HLODs, it increases the size by 22 megabytes. Now, let's go ahead and look at them. You can click off Show HLODs and Editors in your editor preferences. Then you can go click on the pawn next to the HLODs that will pop up in your editor, and you can actually turn them on. You can go down there and hide the rest of the scene. So let's see what's going on here. Here's what the landscape is, because the landscape's excluded. And I get asked a lot, and it's a good question, like, should we include landscape in the HLODs? Sorry about that. It's optimized already. So near the camera, we have more triangles. As you go farther away from the camera, the triangles reduce. It's meant to be there all the time, and it's meant to make it cheap far away. So if you try to shove all these triangles then into your HLOD, it really increases the size. This is a lot of small, fine detailed data. So here's what our merge mesh for Tilted Tower looks like, plus the trees, which are actually instance 3D imposters. And here's what the terrain put on there. So this is just what you would see without any actors or component loaded in. And you can see here what's excluded. So these items in yellow over here are actually the actors that were not checked to be included in HLOD because they're just too small. We want to reduce that data, make the HLOD smaller. And here's just a side view, just to sort of like see inside of a building and see that it's very empty. Also, the textures are reduced. The model's reduced. It's all about getting rid of that data far away so there's less to process. There's what they look like is missing. Here's the size for a default cell. So like what's it actually generating? And you can see outlined over there the meshes that are actually there. So what happens if you click on your HLODs, you can go up to the mesh, go down, actually find it, and we'll actually look at the individual impacts in our file. All these to make up that amount. So details, let's go look at it. 3.5 megs to make that building there and these sidewalks. 4.2 for these buildings. 3.8 for just that little shed over there. Just sort of showing you, this is just going in your package size because you're using HLODs. Merge mesh HLODs, and we'll talk about the rest. A meg for that building. And this would be like a custom asset. This is literally your custom asset for your level. Trees, teeny. Well, we got that little sidewalk there that's involved. A little piece of this barrier here, 3K. So you see, this is just increasing your package size. And water even is in it, or that little water pond over there. What's up with the trees? These beautiful trees can be instanced. So that means we can put a whole bunch out there. But they wouldn't be interactable at this point. But that's a really nice part. And we've known that about Fortnite. So no HLODs, we got 46 megs. This is what it would look like if you could instance HLODs, if the materials did sort of play along. Because they're all black because they're world grid materials, because UEFN props do not have instanceable checked off on their materials. That's simple change. But what I'm really trying to show, 46 megs, 54 megs, how much smaller ISMs are. We can override the material on the props, but it won't make it to our HLODs, sadly. If you wanted to then, say, replace the UEFN props with your custom assets. So then you can use ISMs. You could create your transform at the exact same spot as the UEFN prop. Then you can go ahead and, well, there's a couple, drag it out into the world so that now is your recently placed item. Then you can select all of those meshes and do a replace with recently placed and just do the whole piece. So this is about rapidly replacing lots of UEFN props with custom props, and then you can use instancing or just bulk editing. Because we need that little checkbox in the material used with instance tag meshes. Once you do that, you can then select these meshes that you have in the world, go through modeling mode, and pick the harvest instance to make your own instance without having to place the pieces. So it will make an ISM for you. I normally uncheck the delete inputs, because then if you want to save those custom meshes you place somewhere else, so you modify them later and redo this process, rather than messing with moving ISM instances, you have the option. So not to delete the source. So we have the original merge mesh HLOD for 68 megs. Let's make it bigger. Let's just make 6 times more instances up in the world. Now, I didn't bring in the actors that were excluded from the HLOD. It's just more of what is included in the HLOD. So we have 163 megs is now the size of the package, or the folder for Tilted Towers. If we instance it, we get 30 extra megs. So I have a good chart later to show you, but showing you what's missing. We get one-to-one mesh matching, and if the texture just had that used with instance on there, it would look exactly the same. We could also use merge mesh, and this is what the merge mesh would look like, 100 extra megs. So instead of 30 megs for ISMs, we're having to deal with 70 extra megs for the extra piece because we're using a merge mesh, more triangles, more data. And here's just showing you the size of the cell. And we do have an option for voxel simplified, if you've seen that. This is basically trying to make the merge mesh have less triangles, and it does reduce the amount of size. So here you can see the difference between merge mesh and then the voxel simplified. And I did come out there. It does look bad or worse on this side, but it's a good savings in comparison. And what it does is it gets rid of triangle data. So we're reducing our data down, so then everything runs quicker. And here's the comparisons. Base, 30 megs if we were to instance it. If we just did voxel, that means that the reduced one, we can get up to 57 megs. So that's pretty good. We're saving 50 megs if you want to do that piece. Oh, and talk about the size, because it's going into your 2 gig upload. So your merge mesh HLOD, any of these things, it's going into that. And your final download size. Here's how you could change it to use the approximation mesh. You would make your own HLOD layer and then assign it in your world settings. So you could use some of those different fine settings there. And then you go in and select it in your HLOD layer on your actual actors to ensure that's there. And that would be if you wanted to use that reduced HLOD setting. Let's look at the grid sizes. So you can turn on grid preview in your world settings. Then you have your grid cell is your size of what the merge mesh becomes. The distance loading is where we're going to bring actors in and get rid of them. So you can play with that a little bit. The bigger they are, the more unification we get, rather than if you have smaller cells, you're going to have more cells, it's more components, it's more data. So there's a balance there of less components, less data. I covered that, loading distances. Draw distances can reduce rendering of spatially loaded actors and other static mesh components. But if you edit them, here we go, then they're going to be reset. So if you go into live edit and you go to move something around that you did adjust, it pulls in a new template. Custom assets, they let you adjust, who wins versus UEFN props versus custom assets. For mesh complexity, you can change it on custom props. You have that access. But with using UEFN props, you're going to be stuck with the LODs that they have in there. So you can think about, do you need LODs? Do you need LODs, or is that window without shutter, whatever it is, good enough? Then get rid of the other 3 pieces of data on your custom assets. You can do it. So it's all extra cycle time, the more triangles you have. With textures too, so we're going to look at your material complexity. If you can use channels some texture UEFN prop materials can be replaced. So like when you're replacing that material, it's going to increase your package size, but you want to think, is it a simplified material for rendering on the client? So like if you have a really complex Or can you use one texture? So using multiple channels and packing. Texture packing is a typical thing to do. Rather than having 3 textures, to use the green, the red, the blue, and the alpha channels of that one texture. It's the same size of an image, rather than having 3 images that you're not using those channels on, and they're just wasted. So all the images have those extra channels you can split out. Shader instructions, that's what's going on in your material graph. It's taking all that data from the individual textures, doing work on it. So the more you have, the more work you're gonna have to do, the longer those cycle times take. So you can pack in more textures in the same size by making these atlases, or just having smaller textures in that same amount of workload, rather than having to, I mean, if you just, everything's 2K, it's a lot of extra workload, even with virtual textures being enabled for Fortnite. And so texture size, reduce those down as well. A custom material, you may not have any textures in there. You may be able to do it all with code, then you're not gonna have that data piece there. You're just adding instructions, that's lighter. So consider, do I need textures in here? If I'm just making it red, can I just put a constant red node in there rather than have a red texture? And some people, or do you want that extra depth? So how to reduce stuff on meshes? Here's a typical cube. Make less triangles. And that would be less data to cycle. So try to reuse it too. So we have 2 triangles. We could bring it out, and this is custom modeling stuff. Bring it out to give us some extra character to our square, and still reusing the same amount of faces. So going from 15 triangles to 10, but getting more character out of it. This is something I learned working on Counter-Strike back in the day, trying to deal with low amount of triangle and giving extra character. Same thing, only we couldn't really do anything. So I want to say thank you to my mentor on that, Justin, for nothing. So here's all of your data cycles from everything going on. Anything you cut out, anything you're checking off, is getting a little bit of that data out of there, so the cycle will happen faster. So how to place less actors, or how to do less data. I'm just going to go through some basically quick hits here on things to do. Use larger props to fill the area, rather than having multiple components there or multiple actors. Use custom instance static meshes if you can, like the ISMs, rather than using multiple components, and place that out, because that reduces the data down, lets you do batching. Static and non-static actors can support ISMs, meaning that you can build your ISM and put it on a movable actor. That reduces the amount of components on that actor, so reducing the data using that ISM, even though it's moving in the world, so they don't have to be completely static. And you only want to use ISMs if you have more than 2 instances. So there's a cost, which is the array of locations. And so if you only have 1 ID in that array, you're still getting the extra cost of having an array. So a single static mesh is better than an ISM if you only have that mesh once in your world. Otherwise, otherwise a single static mesh is more important. Merge multiple static meshes into a single one. So if you don't use it as a kit batch anywhere else, so you have these 4 meshes that you only use in this one place, merge them into one, it becomes one component, because you only use it once. And that reduces the amount of complexity. Use less components per actor. So if you can, pull it out. Disable components you don't use, so those are the checkbox we were talking. On UEFN props, on anything you're doing, clear variables that you don't need. So if you're not using the sound or you're not playing the sound, get rid of the sound file in there so it can't reference it, can't consider it. And use static mesh components in place of multiple static mesh components, or ISMs. Reuse assets in your level. So one of the biggest things is you're putting stuff into memory. If you put 12 different walls of the same white brick, you're going to have all that extra stuff to consider in memory when you could use just that one wall. So if you can deal with the art direction, not having so much complexity in your environment, reduce it down, it will lighten up the amount of cycles, lighten up the amount of data, lighten up the amount of instructions. So reuse your materials and textures as much as you can. Simplify the scene down. Disable. And reduce configurations on props to only meet what your requirement is. So if you don't need damage system on the prop, like we talked earlier, just go ahead, turn it off, or get a simpler piece. Use systems that automatically unify the systems, like the HLOD system. Use it. So what's rendering versus game code? Visual assets versus devices, and reverse. So I have the device over here, and game code makes changes to the environment, actors or gameplay during runtime, and that requires cycling. So network CPU, that's what game code does. Visuals, that's just the end result that you're rendering on the client. So your CPU is taking care of gameplay code mostly, and then your GPU is taking care of visuals. So what's rendered? So rendering is the end result from gameplay, like presented visually for consumption, each frame or tick. Game code is only visually seen when it's rendered. Rendering is client-side only. You don't have GPUs on the server. UEFN props are considered gameplay code because they're interactable and changeable. So they're going to impact, and if you don't need a UEFN prop, but you just want the visual there, make it a custom device or look at that to get rid of that extra cycle, disable those pieces. So an example of what could be static versus non-static, systems that can save cycles by being cached. So a mountain, we may not need to ever mark that movable, but maybe you do generate your terrain. Maybe you do move a mountain. So it's up to your environment. But if you don't need to move the mountain, disable collisions on it if you never get there. Disable overlaps on it if you're never going to overlap with it. In the starting, think about, my environment's made out of these things. What do I not need? Why is it enabled by default? Because it's not being thought of on Epic's side. It's a general purpose environment. So network movement as well. So when you have it marked as movable, it's seeing if it ever moved and sending it across the network. So by being static, it won't be checked to see if it needs to be moved or moved across the network. Shaders, mesh distance fields, using it, effects, any of these things are going on. It's like, do I need this mountain to have mesh distance fields enabled on it? Just every little piece. So does it need to catch the shadow? Because I see the shadow of the mountain. And because shadows are dynamically generated in Fortnite, there's no real cache in there because of the movable light. Nav mesh. Do AI get to the mountain? You know, does it ever get able to affect, or does this tree, should it stop AI? Physics is coming up, if I put it in there. Should it affect physics? Should it have continual collision detection enabled on your mountain? No, because that's saying this mountain, if it was to enable physics, must be considered every frame fully. So it's just, that one there when I saw it, I'm like, wow, why is this a thing? You don't even have physics. Oh. Sorry, I was looking at the wrong stream. So physics is now up there. So static versus non-static. Static means it will not change during any gameplay. It's fixed or stationary, lacking movement development, showing no visual change. Your buildings and your trees, they might not be static, or they could be. Maybe you don't want people destroying your building. Don't want them destroying your trees. That would also save. Or maybe you do want to harvest your trees. Maybe you are going to build, and you do need that. What definitely is not static is stuff that has been built during game, or of course items down here. These are things that have to be moved. And I'm really saying there, consider everything you put into your world if it can be static, hence reduce the amount of things on it, or if you're going with that full interactability. And even if it is that full interactability, look at it and look at disabling things that you don't need. Always reduce instructions. Oh, wow. We're going to be able to do maybe some questions. This is great. I also have YouTube up here, Game Dev Micah, 2 hours of 20-minute videos going into every little box, walking through the editor. So that would be if you want to go in more depth on it. Here's some great videos I'd like you to watch, which is UEFN Management over there by James, and Julian over here for Project Optimization, if you haven't seen these, and How To Boss does a great way on data layers. So that's what I'm going to say is watch How To Boss's video. CleverLike, hopefully you know about CleverLike and Asion. Great videos you can watch for tutorials as well, I'd recommend. So less is best, but not less of you. Thank you for coming here. It's been so cool to hang out with all of you guys. And also this wonderful crowd here, everyone.